present. So even after forest fire, so this rhizome only long last and can develop the new plant. Able to understand? So that long last part of the plant is the rhizome only. Able to understand here? Next one. So this stem is also having the what we can say the leaves are present. In the stem also what steel. Steel is very important. What type of steels are present? Here protosteel, siphonosteel, and solenosteel, and dictyosteel. So different types of steels are present. Protosteel, you know well, what are the examples for the protosteel and siphonosteel and solenosteel and here dictyosteel. So example for here protosteel or what Selaginella, protosteel, Selaginella. These are very important, man. And siphonosteel, Osmunda, and the solenosteel, fence. Solenosteel is present in the fence, and Diopteris and Pteris, dictyosteel is present. Diopteris and Pteris. The types of steels are very important. Note it. Right. So root, stem. Next part is the leaf only. So leaves are pinnately compound leaves are present. Pinnately compound leaves. Compound leaves are present. Okay. So these leaves are small to big leaves are present or large leaves are present. In Selaginella, small leaves are present. Selaginella. And big or large leaves are present in the ferns. So the range of the leaf is also small to big. Right? Next, here on the stalk of the leaf. So here the petiole, we can say that. So the leaves are pinnately compound leaves. It's called as fronds. In the ferns, the leaves are called as fronds, and these leaves bearing sporangia are present. The sporangia bearing leaves are called as sporophylls. Understand? So what type of leaves are present in the pteridophytes means spore bearing leaves are present. So that they are called as sporophylls. Where the sporangia are present? On the abaxial side. Abaxial means what, ma? Abaxial side. Lower side, sporangia are present. So these sporangia are present in a group. Group of sporangia is called as sorus. A group of sorus is called as is called as sori. Did you understand my here? So one sporangium single. Okay, now many sporangium are together called as sorus. Many sorus together called as sori. So the sori is present on the lower surface of the leaf. Just note it down. We'll explain that. Yes. Here on the petiole also brown colored hair is present. What is the name of brown colored hair? Ramenta. Ramenta. It is very important. On the stem is also, on the stem also, the brown hair is present. Ramenta is present. Right? Say yes. We'll wait for your message, ma. Right, ma. So here, in some plants, in young stage, young leaves are coiled inwardly. Coiled inwardly. That coiling inwardly is called as succinate vernation. Succinate vernation. Vernation. Actually, vernation means formation of new leaves. Formation of young leaves. Young leaves is called as vernation. But succinate vernation means coiling of young leaves inwardly is called as succinate vernation. So it is the main characteristic feature of the ferns. Main characteristic feature of the fern. Okay, Nama? Right. Here, if you see the leaf, so leaf is present like this, no? So here, lower side of the leaf, for example, abaxial side, if you see, so if the leaf is, it is the lower side and it is the upper side. Now we are taking upward direction. Able to understand? Upward direction. For example, if it is the leaf, upper surface and lower surface. Now we turn the leaf like this. Okay, now so lower surface is coming upward and upward surface is when we reversed, when we place the leaf reversibly, the lower surface will come upper surface will go lower. Now it is a lower surface. Okay, now you don't think that why Sar is showing up upwardly and telling that the lower surface. So now we turned the leaf like this. So before the leaf will be like this. Now we turned it. So lower surface came upward. So now we are observing the sporangia. So sporangia are present at the leaf margins. So at the near the margins, the sporangia are present like this. Black or brown spots are present. Brown or black spots are present. So these are called as sori. Sori. So each sori. So here it is the sori. Here many soras are present. Many soras. In the soras, what are present? Sporangia are present. So sporangia, soras, all together called as sori. Did you understand here? Soras, sori, and sporangia. Sporangia. So inside the sporangium, so the spores are developed. Now we are taking this one sporangium. So inside the sporangium, spores are present. Spores are present. Sporangia is developed in two methods. What are they? Leptosporangia and eusporangium. Eusporangium. Leptosporangium and eusporangium. So if the sporangium is developed from a single leaf cell is called as leptosporangium. You able to understand, ma? So development of a sporangium from a single cell is called as leptosporangium. And development of sporangium from a group of cells, a group of cells is called as eusporangium. So example for leptosporangium. Leptosporangium example. Leptosporangium. Dryopteris, Marsilia, Dryopteris, Marsilia, Osmunda, and here Salvinia. Right, examples for leptosporangiate. Okay, Nama. So Salvinia also you can write Salvinia. And next, eusporangiate. So in which plants the leptosporangium is present means Dryopteris, Marsilia, Osmunda, Salvinia. And eusporangia is present. Eusporangia or eusporangium. Eusporangium means what? The sporangium developed from a group of cells. Okay, Nama. Here Xylotum, Equisetum, Xylotum, Equisetum, Equisetum, and Selaginella. Selaginella. So these are very, very most important points. So in which plants the sporangium is present, leptosporangium and eusporangium. Right. Based on the type of spores, the plants are divided into, here the spores are produced in the sporangium is covered by where the sporangium is present. This is the marginal region. So here the sporangia are present. Sporangia are present. So these sporangia are covered by a thick layer of cells. The thick layer of cells. It is the kidney-shaped covering. Kidney-shaped covering. So this is called as indusium. Indusium. Okay, Nama. So indusium means a covering. A covering present over the sporangia is called as indusium. Sometimes this covering is absent. Only the leaf margin itself forms a covering. So this is called as false indusium. Did you find it out? The difference between the, if covering is present, true indusium. If covering is absent and then only the leaf margin forms a covering is called as false indusium. False indusium. So indusium is present in the terrace. And other plants, false indusium, Selaginella, like that. Okay. Are you clear with this? So what is the indusium? What is the false indusium? Indusium means a covering over the sporangia. Next one. Type of spores. Here inside the sporangium, if same type of spores are produced, same type of spores, that producing the same type of spores is called as homosporous. The plants that produce same type of spores is called as homosporous. Example for homosporous, Dryopteris, Lycopodium, Teres, Equisetum, Selaginella. Okay, now homosporous. You can write here homosporous. Based on the types of spores produced in the sporangium, the plants are divided into two types: homosporous plants, and heterosporous. Homosporous plants means produces the same type of spores. And two different types of spores are present. So two types of spores are produced. What are they? Microspores and megaspores. Megaspores. Microspores and megaspores. Two types of spores are present. Here only one type of spores are present. Here homosporous plants examples, Dryopteris. Dryopteris. Best example for homosporous. Lycopodium and Pteris. Lycopodium and Pteris. So Pteris plants are also example. Equisetum, Xylotum. You can write some more also. Equisetum and Xylotum. Xylotum. So all these plants are example for homosporous plants and heterosporous plants. So Azula, Selaginella, Marsilia. So here you can write. So blind symbol for this Mars. So Mars means what here? Marsilia, Azula, Azula, and Selaginella, Selaginella. And another one is Salvinia, Salvinia. So these are very important. What is meant by homosporous and heterosporous? You note down. Okay, if it is completed, say yes. Homosporous means same type of spores. Heterosporous means two different types of spores. So what is the shape of the inducium means? Kidney shape. So in Pteris, inducium is present, true inducium. Okay. Still writing. Right. Are you clear with this eusporangia and leptosporangia and homosporous and heterosporous? Right. Is it completed? Make it fast, ma. So the next one is so spores are released. Spores are released when the sporangial wall is gets a break. So the spores are released. So spores actually in the sporangium, sporogenous tissue is present. Sporogenous tissue. So this sporogenous tissue is diploid in condition. Diploid in condition. So these cells are developed into spore mother cells. Spore mother cells are undergo meiotic division, meiosis, and produce as a haploid spores. Haploid spores. So that haploid spores are either same type or two different types. So after the releasing of the spore, so when the annulus is present here, the annulus is a breakdown, the spores are released, and these unicellular microscopic haploid spores are germinate. They germinate the structure, multicellular autotrophic structure. Autotrophic structure is developed. So by mitotic division, so this is the spore. It undergo many times mitotically divide and produce a multicellular structure. So this multicellular structure is present in the heart shaped, but it is a independent, free living autotrophic multicellular structure. Autotrophic, heart shaped, free living multicellular structure is called as gametophyte. So gametophyte. From where the gametophyte is developed? From the spore only. How the spore develops into gametophyte means that by mitotic division. So this gametophyte is of two types. So it is a gametophyte. Many cells are present. Many cells. So here gametophyte is of two types. What it is a monoecious gametophyte and dioecious gametophyte. Monoecious and dioecious. Monoecious and dioecious gametophyte. Monoecious means in this gametophyte, two types of sex organs are present. What are the sex organs here? Can you say sex organs? Antheridia and archegonia. So like bryophytes, here also male and female sex organs are present. Female sex organs. Male sex organ is called as antheridium. And female sex organ is called as archegonium. Okay, Nama. So here the difference is in between the bryophytes and pteridophytes. In the bryophytes, the sex organs are having the stalk. So stalk means you can understand. For example, archegonia you take. Here this is the stalk is present. And then here neck and venter is present. But here in pteridophytes, this stalk is absent. Archegonia is present, venter and neck, but the stalk is absent. This type of sex organs are called as sessile. Sessile sex organs are present in the pteridophytes, and stalked sex organs are present in the bryophyte. That is very important point. Are you clear with this? So what is meant by the sessile sex organs or stalked sex organs? Sessile sex organs means without stalk, the sex organs are present. Antheridium is also. So here in the bryophytes, if you see, the stalk is present on this club-shaped structure or developed. So here this is the stalk, but in the pteridophytes, this stalk is absent. Only antheridium. So the club-shaped is present. Okay, Nama. So these two are sessile sex organs, but these are covered by sterile jacket. A multicellular sterile jacket is present. Multicellular sterile jacket. Here also, multicellular sterile jacket is present around the sex organs. No difference in between the bryophytes and pteridophytes. Only the difference in the sex organs is the Sessile sex organs are present in the pteridophytes, and stalked sex organs are present in the bryophytes. That is the difference. That's all. Remaining same. Okay, right. The male and female sex organs are present on the same gametophyte. Here, the gametophyte is also having what rhizoids. Rhizoids are present. They get contact with the soil by the rhizoids only, but heart shaped. All the cells are haploid in condition. Why? Because it is developed from the haploid microspore. Okay, now. So that means haploid spore, not microspore, haploid spore. Okay, and here the sex organs are present. Archegonia. So this is the archegonia. Stalk is option C, and then antheridia. Antheridia. So if archegonia and antheridia both are present on the same gametophyte, then it is called as monoecious. What is the example for monoecious? Lycopodium and equisitum. So example for Lycopodium and equisitum. Equisitum. Best example for monoecious condition. And dioecious condition. That means on two different gametophytes, the sex organs are present. So here I told that what two types of spores are present: microspores and megaspores. Microspores get germination and develops the male gametophyte. Male gametophyte. Gametophyte. So here it is the male gametophyte, and megaspores develop and produce the female gametophyte. Female gametophyte. It is the female gametophyte. Did you catch the point here, ma? So microspores germinate and produce male gametophyte. Here also multicellular autotrophic structure, and it is also multicellular autotrophic structure. But on what basis we can say? So here rhizoids are present, rhizoids, and here also rhizoids are present. On what basis we are telling that the male gametophyte and female gametophyte means? Here the male gametophyte consists only antheridia. Only antheridia are present. Antheridia. But female gametophyte consists of only the archegonia. Only archegonia. So how did you, how can you define that male gametophyte and female gametophyte? The male gametophyte means the gametophyte with the antheridia are called as male gametophyte. So it is a free living, independently living autotrophic structure or stage of the pteridophytes. Here also independently living. The female gametophyte means the gametophyte which bear the archegonia are called as a female gametophyte. So these are separately present, but here combinedly, archegonia and antheridia are present combinedly on the same gametophyte. If they are present on the same gametophyte, monoecious condition. If they are present on two different gametophytes, it is called as a dioecious condition. Monoecious and dioecious. Example for dioecious, what ma? Marsilia and Selaginella. So for dioecious, Marsilia and Selaginella. Are you clear with this? So note it. Make it fast, ma. You are sending the message very lately. Right. So actually, here what happens? Antheridia produces the male gametes. Male gametes. So these male gametes are multiciliated. Multiciliated. Multiciliated spermatozoids or male gametes. Where in bryophytes biciliated. only two cilia are present or two flagella are present. But here many cilia are present. Okay, Nama? And these are female gametes. Female gametes. So female gametes are present in the okay, Nama? So at the time of fertilization, the neck canal cells and ventral canal cell are disappear and passage is formed. Then the male gamete enters. So for fertilization, what is required here also? Water is required. Water is essential for fertilization. So the pteridophytes are also dependent on water for fertilization, like bryophytes. So this male gamete swim in the water and reaches the egg cell and fertilizes. So it produces the zygote. Zygote is produced. This zygote is developed in the archegonium only into embryo. That embryo that is called as what, ma? Sporophyte. So here this sporophyte is produced as what is. So sporophyte. So generally, the sporophyte is also developed in the archegonium. Okay, now again this sporophyte bears leaves and leaves having the sporangia. Sporangia produces spores and spores undergo meiotic division. That means spore mother cells undergo meiotic division and produce the spores. Spores get germination and gametophyte is developed. But the main important here, the gametophyte is also called as prothallus. Prothallus. Another name for gametophyte is called as prothallus. So prothallus structure is absent in the Salvinia. The prothallus structure is absent. Okay, able to understand? So here the gametophyte having the sex organs, and sex organs produces the gametes. Okay, by which division the sex organs produce the gametes? By mitotic division only. Sex organs are haploid in condition, so they undergo mitotic division and produces the haploid gametes. Okay, now that gametes are fused together to form diploid zygote that develops into embryo. Embryo develops into sporophyte. Okay, Nama. So sometimes what happens is, see, generally sex organs produce the female gamete and antheridia produces the male gamete. That two gametes are fused together, but directly the cells of gametophyte, here it is very important, epogamy and epospory. Epogamy and epospory are very important points. Epogamy means, actually we are telling that this is the gametophyte. Here sex organs are present here, but sometimes what happens, the cells of gametophyte develops into mother cells, and they directly use the sporophyte. So some cells of the gametophyte directly gives the sporophyte development. Sporophyte is developed. Sporophyte is developed from the cells of the gametophyte. That means without gametes. So no sex organs here, ma. No sex organs. So involvement. Only directly the cells of prothallus. What is the condition of the cells of the prothallus? Haploid in condition. These haploid cells directly divide mitotically and develops the embryo. So the cells of prothallus are gametophyte. Undergo mitotic division, mitosis, and produces the embryo. So this embryo develops into sporophyte. Are you clear with this? Sometimes only in some plants. So that is called as epogamy. Epogamy means the process of development of sporophyte directly from the gametophyte without formation of gametes. You write down, epogamy means development of development of sporophyte from gametophyte. From gametophyte. So this is the gametophyte. Directly, no gamete formation. Directly the gametophyte is developed into sporophyte. That is called as epogamy. Epo means without, gamy means gametes. Okay, Nama, without formation of gametes, gametophyte is developed into sporophyte. Okay, now next apospory. Apospory. So actually, sporophytic stage is present. So this is the stem, and these are the adventitious roots. And here leaves are developed. Leaves are developed. So this is the sporophyte of the fern. So here, sometimes what happens, the cells of sporophyte directly develops, mitotically divide and produce. What type of cells are present, haploid or diploid? Diploid cells are present or haploid cells are present in the sporophyte? So diploid. In the gametophyte, haploid cells are present. Gametophyte, haploid cells. Sporophyte, diploid cells are present. These diploid cells undergo mitotic division. And produces embryo. So what type of embryo is produced? Diploid embryo only. And this embryo is developed into so this gametophyte is a diploid in condition. So that means sporophyte without formation of no spore formation, no spores are produced. Sometimes only this process occurs. So the sporophyte develops directly into gametophyte without formation of the spores. That is called as apospory. Are you clear with this? So actually here, in the normal condition, sporophyte is sporophyte normally. So you can write normally. Sporophyte is a diploid in condition, and gametophyte is a haploid in condition. Okay, now in rare conditions, what are the rare conditions? Apogamy and apospory. Apogamy. So you can write apogamy. By the apogamy, what is produced? Gametophyte is developed into gametophyte develops into here this sporophyte is in haploid condition. Sporophyte is haploid condition. Next one, apospory. And the apospory means what? The sporophyte develops into gametophyte. Here actually sporophyte is in diploid condition. The produced gametophyte is also diploid in condition. It is the rare condition, abnormal condition. In this apogamy and apospory, the ploidy of the gametophyte and sporophyte is reversible. Are you clear with this? Apogamy and apospory. So in which plants it occurs means apogamy and apospory occurs in bryophytes and pteridophytes. Bryophytes and pteridophytes. So well, here you need to remember the main important points, types of steels in the stem, and then leptosporous, and then homosporous and heterosporous, and then what monoecious and dioecious. So that important concepts here. Next one, classification of the pteridophytes. Classification. So the pteridophytes are classified into different classes. What are they? Here well. Can you say Psilopsida, Lycopsida, Sphenopsida, and Pteropsida? Okay, now so different classes. First one is Psilopsida. Psilopsida, Lycopsida, Sphenopsida, and Pteropsida. So in the Psilopsida, Xylotum. Example for Xylotum and Rhinia. Sometimes they will ask what are the examples for Psilopsida class. Okay, Nama, Xylotum and Rhinia. Lycopsida, you know well. What are the example? Lycopodium, and Salacinella, Sphenopsida, Equisitum, and Pteropsida. So here Adiantum, Azulla, and here Pteris and Dryopteris. So all are example. Marsilia. All are example. Right? Next one. Life cycle of the pteridophyte. So we can observe two types of life cycles in the pteridophytes. So two different modes. Okay, now? Is it clear? Can I write this one? Right. So if you observe, in some plants, the sporophylls are also compactly arranged and produces the what stabili or cones. Cones are present in the equisitum and Salacinella and Lycopodium. Cones are present. A compact of sporophylls, cones are present.
Sir.
In the fence. Hello.
Sir.
Dharni Velan.
Sir, your board is not clear, sir.
Board is not clear.
Letters are not visible, sir.
Okay, right. Now only it happens from the beginning. Dharani Velan. Not answering. 5 minutes. Say in voice. Say. Dharani Velan.
Sir.
From how many minutes back onwards?
Sir, 5 or 10 minutes, sir.
Now you are telling that immediately you have to inform now.
Sir, I think here net slow.
Yes.
In my area.
Yes, that is the main problem. Okay, now it is clear only. So again, I brought the camera close to the board. Is it okay now? You see, just observe.
Little okay, sir.
Little okay, na?
Yes, sir.
So if I bring it very close to the board, so all the board cannot be covered. Okay, na?
Okay, sir.
That means I will write big letters. Okay?
Okay.
All right. Life cycle. Life cycle. So if I write the big letters, what is the problem means? So entire concept cannot be covered. Right. Anyhow. So what is the dominant phase in the pteridophytes? Dominant phase is the sporophyte only. So sporophyte. We will start with the dominant phase. Sporophyte. What is the ploidy of the sporophyte? Diploid. First, we will discuss the life cycle in the Homosporous. plants. Homosporous life cycle, heterosporous life cycles. Two types are there. Okay, na? So sporophyte are produced. So sporophylls. Sporophylls are produced. So in these sporophylls, what are produced? Sporangia. So sporangium is produced. Here in the sporangium, spores are produced. Spores. By which division? Meiosis division. By meiosis division, spores are produced. Here all the cells are diploid in condition. Diploid in condition. So when the meiotic division takes place in the sporogenous tissue of the sporangium, it produces the haploid spores. So these haploid spores germinate. That means by mitotic division, mitosis. And what is developed? Gametophyte is developed. Gametophyte. So in the gametophyte, what are the sex organs are present? Male sex organ and female sex organ is present. Female sex organ. So male sex organ and female sex organ. Okay. Female sex organ produce the egg cells and male sex organs produce the male gametes. Male gametes. So these two cells are fused together. That process is called as fertilization. Fertilization. Right? Here, what is developed here? Zygote. Zygote develops into embryo. So embryo develops into what? Sporophyte. Sporophyte. So this is the life cycle seen in the homosporous plants. So from here, gametophytic stage. So from the spores up to the formation of zygote. Here, this is the gametophytic stage. Gametophytic stage. And it is the sporophytic stage. Sporophytic stage. Able to understand? Sporophylls. Next, in heterosporous, it is different. Here, nothing but here two microsporophylls and megasporophylls. Okay, now the gametophyte is different from the starting itself. Okay, time is up now. What is the time now still? Yes. So now I'm ending ma.
Good morning to one and all. Good morning, ma'am. So today we are going to discuss in chemical bond some more here additional points. So here today we are going to discuss here hydrogen bonding, so intermolecular courses and whatever that one others. So see that one. First of all here hydrogen bonding. So hydrogen bonding, what type of questions they will ask that one regarding to this concept one. So here hydrogen bonding, generally you know that one. Yesterday I explained that one between hydrogen atom and highly electronegative atom. So highly electronegative atom means fluorine. So that is nitrogen. And this one is oxygen. So very rare case fluorine. Rare case. So like that here, highly electronegative atom. That one is small sized atom. So it is contains at least one lone pair and attached with hydrogen. This condition hydrogen bond is possible. So here tick that one. Where is hydrogen bond is possible? So which condition hydrogen bond is not possible? Just you tick that one now. So by here HF condition hydrogen is bond possible or not? Possible means give tick mark. HF condition possible or not? H2O condition possible or not? Ethyl alcohol condition possible or not? Okay. Fourth, here alcohol plus water. Alcohol plus water condition hydrogen bond is possible or not? Alcohol and water. So acetone condition possible or not? Acetone. So that is only acetone you take here. Acetone. So acetone means acetone molecules. This condition hydrogen bond is possible or not? See here, check that one. First condition. First condition, HF condition possible or not? Possible means put the S mark. Not possible means N. HF condition hydrogen bonding is possible or not? Dharni Velan, Achana Gayatri. Press the mark. Possible, very good. So here why that one is HF, this one is, so like that here HF molecule. So this is a more electronegative atom attached with hydrogen and the lone pair is also there here. This one is lone pair seizure possible. Right. H2O condition. H2O possible. Alcohol condition. H2O means what is that one? H2OH like that here H2OH. This condition also hydrogen bond possible. So H2O condition hydrogen bond is possible. H2O water we are taking. H2O water is there. H2O ice is there. So H2O water is enabled to form number of hydrogen bond in water. This one is 1. This one is 2. So H2O condition. So H2O water. So number of hydrogen bonds. Number of hydrogen bonds is equal to 2. But regarding to H2O ice. Size condition, number of hydrogen bonds. So number of hydrogen bonds that is equal to 4. Water 2. Ice is 4. Ice means what is that one? So like that here H2O. H2O means ice structure is special structure. This one is hydrogen bond. This is hydrogen bond. This one is hydrogen bond. This one is hydrogen bond. 1, 2, 3, 4. So like that here ice condition. Each H2O molecule can able to form 4 hydrogen bonds. But liquid state only 2 hydrogen bonds. 2 hydrogen bonds per molecule. Alcohol condition also hydrogen bond is possible. This is possible. Alcohol water condition possible. But acetone condition. So acetone condition hydrogen bond is possible or not? Actually hydrogen bond means the formation of 1 more bonds. That energy above 42. So here how much energy is required? That one above that one is so 42 kilojoule per mole. 42 kilojoule per mole. This much energy produced. Acetone condition hydrogen bond is possible or not? Put the message. Acetone. Acetone means how to draw the one structure. Acetone condition hydrogen bond is possible or not? Yes or no? Dharni Velan. No. What is the reason? So here acetone. So regarding to acetone molecule. So here take that one. Acetone means what is that one? CH3CO. CH3. This is acetone molecule. You take here another acetone molecule. CH3CO, CH3. Okay. Whatever this one is, carbon is positive, oxygen negative, oxygen is negative, carbon is positive. So here this one is what is that one? This is not hydrogen. This condition, more electronegative atom must and should attach with the oxygen. Here that is hydrogen is required in this one. This carbon is not more electronegative. This is sp3 carbon. This is not here carbon. Generally one more thing. So whatever carbon, sp carbon also. Generally carbon size is big. Very rare condition we can see hydrogen bond in HCl condition. Okay. So here this one is carbon cannot able to form hydrogen bond. This is what type of force? Intermolecular forces. Not hydrogen, intermolecular forces. Dipole-dipole interactions. So acetone condition, what kind of forces are there? Intermolecular forces. Getting this point. This is not hydrogen bond. Intermolecular forces means that energy is equal to in between 8 to 42 kilojoule per mole. This is the weakest bonds. So no hydrogen bond here. So by here ammonium cation molecule, hydrogen bond is possible or not? Ammonium cation. Tell that one. Possible means yes, not possible means no. Ammonium cation. No. So here reason what is that one? But here hydrogen, that one is there. Hydrogen, that one is there. On more electronegative atom nitrogen. But here whatever that one lone pair is not there. So here this one is lone pair is required for formation of hydrogen bond with hydrogen atom. So this is no lone pair. So what is the condition? Hydrogen bond. Hydrogen atom present must and should on more electronegative atom like so nitrogen, oxygen, fluorine. That is one condition. Second condition, more electronegative atom must and should contain lone pair. Electronegative atom, hydrogen attached with more electronegative atom. That is must and should contain at least one lone pair. So no lone pair, no hydrogen bond. No hydrogen bond, no lone pair here. No lone pair on nitrogen. So no hydrogen bond. So like that here, hydrogen bond. Hydrogen bond applications are there. So what are the hydrogen bond applications? So different kind of applications are there. So regarding to hydrogen bond applications, see, that is the boiling point, vapor pressure, solubility, viscosity, dipole moment. You can all that one compare that one. Hydrogen bond directly proportional to. So that is boiling point of the liquid. Hydrogen bond directly proportional to viscosity of the liquid. Hydrogen bond directly proportional to solubility. So generally that one is intermolecular hydrogen bond. Hydrogen bond inversely proportional to vapor pressure. So inversely proportional to which one? Hydrogen bond inversely proportional to vapor pressure of the liquid. Getting this point. So hydrogen bond directly proportional to what is that one? Boiling point and also melting point also. Hydrogen bond is there. So melting point is that is also more directly proportional to melting point. So here these are all applications regarding to hydrogen bond. So here you are taking here hydrogen bond to boiling point condition. So take here this one is boiling point, compare that one. Boiling point ethyl alcohol. So this one is dihydric alcohol is there. CH2OH, ethylene glycol, and glycerol, glycerine, trihydric alcohol. CHOH, this one is what is that one? CH2OH, CHOH. Next is CH2OH. So here 1, 2, 3. What is the boiling point order? 1, 2, 3 compounds. Compound number 1, 2, 3. What is the boiling point order? This is ethylene, ethyl alcohol. Second one, glycol. Third one is glycerol or glycerine. So which compound is boiling point is more? Very good. Dharani, Villain, Lakshmi here. That one is very good, ma. Dharani. Right. Archana is also correct. So this one is, what is that one? Number of hydrogen bonds. The number of hydrogen bonds here, this one is OH group is increases. So one OH group, here two OH group, here three OH groups. So number of OH groups are increases. Boiling point increases. Okay. So like that here, we take here that one is regarding to water. Wherever water and next one, generally that is general case. What about on regarding to water, HF? So HF is there and ammonia is there. Generally water. So in HF here HF is hydrogen bond is strong, strength of hydrogen bond. So here that one is 1, 2, 3. This one is second question. Suppose you are taking this is one question. This is another question. Here what is the strength of hydrogen bond? Strength of hydrogen bond. Strength of hydrogen bond. Put the here answer. 1, 2, 3. Strength of hydrogen bond 2, 1, 3. Very good. 2 greater than 1, 1 greater than 3. Why? Because this is HF bond. Electronegativity difference is more. Next OH bond. Electronegativity difference is less. NH bond. Least electronegativity difference. Very good. But what is about on boiling point order? So boiling point order regarding these three compounds. So open to all, anybody, what is the boiling point order? So boiling point order, tell that one. So boiling point here, that is water is highest value. Next one is HF, next one is ammonia. So this is boiling point value, this one is highest value, which one? 1, water. Next one is HF. So next one is ammonia. So that is the reason water molecule. This is more hydrogen bonds. Bond energy is more. This is HF molecule can able to form 2 hydrogen bonds. But NH molecules, so 3 hydrogen bonds. All condition bond energy is not same. NH bonds, HF bond, OH bond, bond energy is different. Okay. So number of hydrogen bonds, suppose here what here we can take 4. This one is 4. So water is generally what we say 2. Okay. But HF is that one is here double number of hydrogen bonds are there when compared to HF here water. And bond dissociation energy also more. So by here boiling point highest is which one? H2O. Next is HF. Next to ammonia. Okay. So next you can compare that one regarding to boiling points, hydrides. So in group elements also you can see that one. Group elements means if the group hydrides are there. 6th group hydrides. So like that here you take that one. So H2O, H2S, H2O, H2S, next oxygen, sulfur, selenium, tellurium. So that one is, so this one is hydride. What is the boiling point order? So what is the boiling point order? This condition 1, 2, 3, 4. So which compound is highest value? So one is highest value. Oxygen, sulfur, selenium, tellurium. Generally molar mass is increases, boiling point is increases. But the least molar mass, it should be least, but not least, highest. Highest is which one? 1. Next highest is which one? 4. Next highest 3. Next highest is 2. This is the boiling point order regarding to H2O, H2S, H2SC, H2T. Getting this point. So why here water is more? Hydrogen bonds. Same concept you can apply that one. Regarding to this one is HF, HCl, HBr, HI. So compound number 1, 2, 3, 4. What is the boiling point order? Boiling point order, compare that one. Boiling point order, HF, HCl, HBr, HI. So topmost is HF. Next is molar mass highest 4. Next highest 3. Next highest 2. Getting this point? Is it clear? Understood or not? Generally, molar mass increases, boiling point increases. But HFO, H2O condition reverse. Reason, hydrogen bond. So like that here, you take that one ammonia. Ammonia, that condition also I can explain that one. Regarding the NH3, PH3, phosphine, arsine, nitrogen, phosphorus, arsenic, antimony, bismuth. What is the order? Somewhere here 1, 2, 3, 4. But here this one is topmost. That one is which one? Nitrogen, phosphorus, arsenic, antimony, bismuth. Antimony means SbH3. Bismuth means you take BiH3. Highest that one is 5 only. Next 4. Next that one is comes with 1. Next 2, 3. But expected it should be least. Somewhat is more. So regarding to boiling point values. So boiling point regarding to different condition. Note down these points. This is 5th group hydrates. This one 6th group hydrates. 7th group hydrates. So exceptionally here HF, here H2O. This one is ammonia, somewhat is more when compared to this PH3 and NSH3. That is the boiling point order. Completed means press the button. Any doubt is there, ask that one. Completed. So what is the reason here? Some exceptions. Reason is hydrogen bonding. Clear? Is it completed? Completed means press the button. Right. So next concept. So here generally chlorine condition we can't see hydrogen bond, but some condition we can see hydrogen bond even though chlorine. So example, what is that one? Chloral hydrate. Chloral hydrate formula CCl3 CHOH, take it twice. CCl3 CCl3, CHOH taken twice. CHOH taken twice. So this compound is chlorohydrate. Generally, chlorine cannot able to form hydrogen bond. This one is chlorohydrate. This condition hydrogen bonds are possible. Chlorohydrate condition hydrogen bond is possible. This is hydrogen bond. So hydrogen bond. This one is hydrogen bond. This condition is possible. Second one. This is exceptional case. Chlorohydrate, exceptional case. Okay. Next we take here fumaric acid, malic acid. So which condition boiling point is more? Fumaric acid, malic acid. You take here that one is right here CHCOH. Oh, this one is what is that one? Malic acid. Right. But another one is fumaric acid. Fumaric acid means COH. This is trans condition. This one is take here. This is trans structure. So one is that one is malic acid. This one is malic acid. Malic acid. Second one is fumaric acid. So where is that one is boiling point is more? What is the reason? Tell that one. Malic acid and fumaric acid. So what is the boiling point comparison? Which compound has more boiling point? General question. So IQ based question. This is based on hydrogen bond. Fumaric acid boiling point is more where? The boiling point more malic acid condition. Here intramolecular hydrogen bond here regarding to check that one. Malic acid, fumaric acid. So regarding to malic acid and fumaric acid condition, you compare that one. So boiling point, which condition hydrogen bond is possible, which condition is not possible. So fumaric acid is here. Okay. So regarding to this condition, so fumaric acid condition, dissociation constant of malic acid and fumaric acid. Okay. Dissociation constant. They are asking here dissociation constant. So not regarding to melting point, boiling point. Dissociation constant. So dissociation constant, fumaric acid is more when compared to malic acid. So here first condition. So what happened that one? Hydrogen bond possible is more stable. So that one is compare the dissociation constant. So dissociation constant, fumaric acid is more. Dissociation constant. So regarding this one is fumaric acid is more. So here reason that one is what happened here. So after removal of this proton, you are getting hydrogen bond. So removal of second proton is very difficulty. So here what happened that one removal of first proton and second proton is easy. So that's why here dissociation constant, fumaric acid that is more when compared to. So this one is malic acid. Dissociation constant comparison. So next one, we take here next property KHF2. This compound is possible or not? This is possible, but KH, so Br2, this compound is not possible. KHI2, this compound is not possible. So what is the reason? So here no hydrogen bond. This condition hydrogen bond formation possible. So what is that one? K plus. This one is so HF. This one is HF. Hydrogen bond F. This one is KHF2. KHF2 condition, hydrogen bond possibility is there. That's why KHF2 molecule possible is there. But KHBr2, KHI2, that compounds are not possible. So next one more property. So based on this one is hydrogen bond. We can compare that one dipole moment values. Dipole moments comparison. See here, dipole moments, how to compare that one? Dipole moment comparison. So here two compounds are given. So like that here, one compound like that here, H, this one is H of is there. Carbon, hydrogen. So next one is fluorine. And second carbon. So like that OH, this is H is there. So second compound, you take that one. Second compound here, this compound. Same like that, this one is that one? First carbon, H, F. Second carbon, H, this is H, not F. This one is not OH, let's change there. So here in compound 1 and compound 2, which condition is hydrogen bond is possible? First condition, hydrogen bond is possible. Second condition, no hydrogen bond. So first condition, hydrogen bond possibility is there. So here second condition, sulfur, no hydrogen bond. This condition, no hydrogen bond. So that's why what happened? So bond angle here. Regarding to first condition, bond angle decreases no. Dipole moment directly proportional to cos theta, inversely proportional to theta. So bond angle where is less? First compound and second compound. Which condition bond angle is less? Tell that one more. Compound 1 and compound 2, where is bond angle is less? Compound 1 is bond angle is less. Why? Hydrogen bond. Hydrogen bond is there. So hydrogen bond is there, bond angle is less, dipole moment is more. So like that here, dipole moment, one compound 1 is greater than that of dipole moment of compound 2. So like that we can compare the dipole moment. Getting any doubt here? Dipole moment comparison based on hydrogen bond. Dipole moment directly proportional to cos theta, inversely proportional to theta. Theta is less, dipole moment is more. First compound is OH, second compound OH, OH, you take one. OH, this is OH, second compound you take here OH, okay. This one is OH and another one is take that one SH. Sorry, OH, you take that one. OH. So here hydrogen, fluorine, hydrogen bond is possible. So here OH group, SH group. OH, SH, oxygen, this is OH, SH group. Between chlorine and hydrogen bond possible here. So here between sulfur and hydrogen bond is not possible. So here sulfur and hydrogen, no hydrogen bond. So like that here we can compare the dipole moment based on this hydrogen bond. So here different type of questions regarding to hydrogen bond. Suppose viscosity, compare that one. Regarding to viscosity, so different compounds H3PO4, H2SO4, so HNO3, like that here compound, I compare that one viscosity. So viscosity, you compare that one viscosity. Suppose here that one is compound is H3PO4. So next one is H2SO4. Next HNO3. Next what is that one HCl. So what is the viscosity order? Hydrogen bonds, that one is hydrogen bond number is more, viscosity is more. So here in H3PO4, H2SO4, HNO3, HCl, where is hydrogen bond number is more. So here in these three OH groups are there. Here two OH groups. Here only one OH group. That is last compound, no hydrogen bond. So here viscosity, what is that one? First compound is more. Next to this one, next to this one, least to that one. Last compound, no hydrogen bond. So here how many OH groups are there? Three OH groups. Three OH groups in the structure. Here two OH groups. Two OH groups in the structure. So here how many OH group? Only one OH group. So here that is last compound, no hydrogen bond. So number of OH groups increases. Number of hydrogen bonds increases, viscosity increases. So over here in alcohol and water, where is viscosity is more? Alcohol and water. Alcohol, water condition, which condition viscosity is more? Water condition is viscosity is more. Number of hydrogen bonds more. That is very good, Dharnivala. So viscosity regarding to water and alcohol, water is more when compared to alcohol. Hydrogen bonds number is more. Hydrogen bonds number is less. So like that here we can compare. That one different type of compounds. Different applications are there. So like that here boiling point values, viscosity. So next to dissociation constant value. Compound existing or not, dipole moment. So some compound hydrogen bond is possible or not. So different type of question they will ask. Definitely they will ask one question. So whatever question you are asking, you have to face ready. Right? Completed means press the button. So whenever completed, press the button. Right now I can go to next one. Next one. So intermolecular forces. So based on intermolecular forces, so what are the main concepts here? Intermolecular forces means this is not chemical bond, but chemical bond means ionic bond, covalent bond, dative bond, hydrogen bond, metallic bond. These are only chemical bonds. Intermolecular forces are weak forces of attractions. So intermolecular forces energy very less. So what is the value? This one is 82, this one is 42. 82, 42 kilojoule per mole. So greater than 42 kilojoule per mole, that is hydrogen bond. Less than 42 kilojoule per mole, that is non-chemical bond, intermolecular forces. So intermolecular forces, different types are there. Chiasm forces, so Debye forces, and another one is London forces or dispersion forces, or that one is weak forces of attractions, or induced dipole, London forces, and like that ion dipole interactions. So like that different kind of intermolecular forces are there. So chiasm. So what is the meaning of chiasm forces? Chiasm. Chiasm forces means what is first condition. So chiasm forces regarding to this condition. So what is the chiasm forces? Okay. So chiasm forces means, so regard this one is chiasm forces. Dipole attractions. Dipole attractions are called chiasm forces. Dipole interactions. Dipole interactions are chiasm forces. So dipole induced dipole. So this one is second one is dipole induced dipole. In dipole induced dipole. Induced dipole. This one is called dipole forces. Last one induced dipole. Induced dipole. Induced dipole. So this one is called, what is that one? London forces. Last one is ion dipole. These are the different names: chiasm forces, dipole forces, London forces, or dispersion forces. So individual, this one is ion dipole interactions. Chiasm forces, dipole. Dipole condition, both the dipoles are required here. This one is like that: positive charge, negative charge, positive charge, negative charge. This type of interactions, negative, positive. Dipoles. Two chemical spaces with the dipoles. Dipole into the dipole. One need dipole is required. So dipole means plus or minus. Into the dipole. At the time of, so here interaction, you are getting that one into the dipole. This one is minus means plus, so this partially positive charge, partially negative charge. This is a dipole into the dipole. Into the dipole means, so at the time of instant, so you are getting charges. So like that here, this one minus, this one plus, partially negative. So this side partially positive, partially negative. Ion dipole. Ion dipole means like that positive charge. This one is interacted with, cation is interacting with that one is dipoles. Dipoles means minus plus minus plus like that. So this type of interaction, ion dipole. So right now here, based on that concepts, they will ask you a question: what type of intermolecular forces are there? You tell that one. Right now I give to you question. H2 plus, that one is Cl2. What kind of interactions are possible? H2 and Cl2 condition. Among this 1, 2, 3, 4, which kind of interactions possible? Hydrogen chlorine condition. Hydrogen is, that is, what is that one? No polarity, no dipole. Chlorine is no dipole. So at the time of interaction, dipole, what is that one? So the induced dipole interaction. That is London. Hydrogen, chlorine, what type of interactions? Induced dipole. For example, H2 plus HCl, what kind of interaction? H2 HCl condition, what kind of interactions? Open to all. This is induced dipole. Element means induced dipole. Compound means dipole. Induced dipole or dipole. This is dipole. So what kind of interactions here? Dipole or dipole, induced dipole. Dipole interactions. HCl, HBr, what kind of interactions? HCl, HBr. HCl, HBr, what kind of interactions? Open to all. This is molecule. Molecule means a dipole. Positive, negative charge. Positive, negative. Dipole. No. London is induced dipole, elementary condition. This one is here actually positive or negative. This is compound condition, dipole interaction, chiasm. is suppose you are taking here next sheet is that one regarding to iodine molecule. Between iodine, what kind of interactions? Iodine molecules, iodine, naphthalene, solid ice, solid CO2. London, very good. This is London type of interactions. London interactions. So here that one is next compound NaCl and water. What type of interactions possible? NaCl, water. NaCl and water. What kind of interaction? This is ion. Na plus Cl minus ion. This is dipole. Ion dipole interaction. Ion dipole. Ion dipole interactions. Next here. Water and alcohol, what type of interactions? Water and alcohol, what kind of interactions or what kind of bonds? Water, alcohol. Water, alcohol, not intermolecular forces. That is hydrogen bonding, chemical bond formation. This is chemical bond, hydrogen bond. Okay, not molecular interactions. Water, alcohol, you don't say intermolecular forces of attraction. That is hydrogen bond. Getting? But according to concept dipole, okay. But here you are getting more energy released. Already you know that one. Between water and alcohol, that is not intermolecular forces of attraction. That is chemical bond, that is hydrogen bond. Above 42 kilojoule per mole energy released. Getting? So wherever you are taking, that one is solid CO2. Solid CO2. See, that is, so here solid CO2 condition. So CO2 molecule, CO2 molecule. What kind of interactions? Molecule dipole interactions. Dipole interactions. So here based on that one dipole interactions, we can explain some of the properties. So take here boiling point value. Boiling point fluorine, chlorine, bromine, iodine. So generally size is more, intermolecular interactions are more. What is the boiling point order? This is seventh group elements, fluorine, chlorine, bromine, iodine, boiling points, fluorine to iodine is increases. Why? Because size is increases. So what happens at one? So here that is, so here one London forces are increases. London forces are increases. This is highest boiling point, least boiling point. This one is gas. So this is chlorine also gas, bromine liquid, iodine is solid. So here intermolecular forces, that is London forces are highest in iodine. Size is increases, intermolecular forces increases. But wherever you are going to 1A group elements, don't compare intermolecular forces. That is here metallic bonding. 1A group elements. Lithium, sodium, potassium, rubidium, cesium. What is the boiling point? So compare the boiling point 1A group elements. So 1A group is lithium. Starting element lithium. Second sodium, potassium, rubidium, cesium. You are writing here boiling point more rare first condition. Here the concept is different. This is based on what the one? Strength of metallic bond. Okay, strength of metallic bond. Based on strength of metallic bond. Metallic bond strength is more lithium. So highest. This is highest boiling point. This one is least boiling point. Metallic bond strength depends upon number of valency electrons and size. Size is small. Metallic bond strength is more. Boiling point is more. Here concept is different. Fluorine, chlorine, bromine, iodine. This is not metallic bond. These are interactions, intermolecular forces. So here intermolecular forces increases. Intermolecular forces increases. size increases, intermolecular forces increases, boiling point increases. Getting this point? Telma. Is it clear? That condition, this condition, concept is different. Boiling point, compare that one. Next one here. So here you take that one. CH3 up. Can I rub this one? Completed means press the button. So is it completed? Hello. So here boiling point comparison. So they are asking regarding to different compounds. So what are the compounds they are asking? CH3 of CH3Cl, CH3Br, CH3I. What is the boiling point order? CH3 of CH3Cl, CH3Br. So here fluorine to iodine increases. Intermolecular forces are increases. So intermolecular forces are increases. What happens? Boiling point value increases. Getting? So next to one more question. Suppose CH3Cl, CH3, CH2Cl2, CHCl3, CCl4. What is the boiling point order? Chlorine, number of chlorine atom increases, boiling point increases. That is another question. But fluorine condition, this concept is not applicable. Fluorine condition, this concept is CH3F, CH2F2, CHF3. This is exceptional case. CF4, exceptional case. This one is exception. So generally size chlorine, bromine, iodine size increases, intermolecular forces increases. Here chlorine, 1 chlorine, 2 chlorine, 3 chlorine, 4 chlorine. Molar masses increases, boiling point increases. But here concept is not applicable. CH3 of CH2 of 2 CH. This one is what is that one? CH of 3 CCSC C of 4. So this condition highest value per CH3 of only exceptional case. So this is regarding to boiling points based on intermolecular forces. Clear? Complete that one. Completed, press the button. So after that, next concept, polarization, magnetic moment, that concept. Say that one. Next concept, polarization. Polarization. So regarding the polarization concept here, check that one more. So here polarization means what is that one? So wherever cation size is small and anion size is very big, this condition, the electron density of anion is dispersed. That the electron density of anion is dispersed, that is called polarization. The power of cation is called polarization. Cation is very small, anion is big, like that here. This condition, what we are getting, this one is generally no dispersion, means this is ionic bond. So wherever that is dispersion, so here cation is coming to nearer to anion. This is cation also dispersion. But anion dispersion is more, like that anion dispersion. So like that we are getting this type of structure. This one is, what is that one? This is covalent bond. Covalent bond formation. This is what type of bond? Ionic bond formation. So here this type of dispersion, when it is possible, cation size is very small, anion size is very big. This condition, covalent bond formation, that is called Pajan's rule. So Pajan's rule condition, covalent bond. So polarization is more. That is polarization. That is expressed in terms of polarizing power. So polarizing power, this is phi. That is directly proportional to covalent nature, inversely proportional to ionic nature. Okay, ionic nature directly proportional to thermal stability. Ionic nature directly proportional to thermal stability. So covalent nature means solubility in water is less. Solubility in water is less. Solubility in covalent compounds, solubility in covalent compounds is more, but water is less. So here, like that, we can explain all these properties based on polarization power. Polarization power means the power of cation distorting the electron density of anion. That is called polarizing power. Polarizing power is more, this covalent nature is more, ionic nature is less, thermal stability is less. So these are the relations now. Right? So here generally with some type of configurations, that is polarizing power is more. So where is polarizing power is more? That is cation electronic configuration. That is pseudo inert gas configuration. Pseudo inert gas configuration is where polarizing power is more, covalent nature is more. So this one is polarizing power of cations. Polarizing power of cations. That is depends upon electronic configuration. So wherever that one is pseudo inert gas configuration. Pseudo inert gas configuration. This condition. So this configuration, pseudo inert gas configuration means what is that one? NS2, NP6, ND10. So here outermost shell is containing 18 electrons, not 8 electrons. This condition, so polarizing power of cations is more when compared to that one is this condition, inert gas configuration. Inert gas configuration means what is that one? Inert gas configuration. So inert gas configuration, compare that one NS2 NP6 configuration. Okay. This pseudo inert gas configuration, or where you can see that one. Example, see take that one. Example, that is copper cation, silver anion, copper, silver, arum. This condition you can see that one. Inert gas configuration, 1A group cation, 1A in sodium, potassium, rubidium, 2A group Mg+2, Ca+2, like that here. So here's polarizing power cations, that is more where pseudo inert gas configuration. That is less where inert gas configuration. So polarizing power is more. Accordingly here covalent nature is more. Covalent nature is more. So based on this concept, you can see that one question. See here, like that here compounds are there, CuCl and another one is CaCl2. Which one is more covalent nature? Covalent nature, which compound is more covalent nature? Compare that one. CuCl2, next one CaCl2. Compound number 1 and compound number 2. Which is more covalent nature? Polarizing power is more. Or pseudo unit gas configuration is there. Covalent nature related to pseudo unit gas configuration. Pseudo unit gas configuration where Cu plus. This is Ca plus 2. This is D block metal ion. That is 1B group. Copper, silver, iron. These elements can able to form covalent. This is more covalent. More covalent. This one is less covalent or ionic. Okay. Copper chloride is more covalent. Why? Pseudo inert gas configuration. NS2, NP6, ND10 configuration. This is ionic nature. Why? Inert gas configuration. Getting this point. Next you take that one more example. So regarding to this one, silver chloride or potassium chloride. Silver chloride or potassium chloride, which is more covalent? Compound number 1 and 2, which is more covalent? Which compound is more covalent nature? Silver chloride or potassium chloride? Press the button. Silver chloride, what is the configuration? Pseudo inert gas configuration. So this is more covalent. This one is more covalent nature. This one is less covalent. Getting this point? Cadmium chloride or calcium chloride? Cadmium chloride or calcium chloride, which is more covalent? Cadmium chloride or calcium chloride. You take here cadmium chloride 1, calcium chloride is 2, which is more covalent nature, 1 or 2? Inert gas configuration is there, ionic nature. Pseudo inert gas or non-inert gas configuration, covalent nature. So cadmium chloride or calcium chloride, which is more ionic nature? Open to all. Which is more covalent? Or more covalent, which one? CdCl2 more covalent. Why? That is pseudo inert gas configuration. Zinc, cadmium, mercury, copper, silver, iron, these are all pseudo inert gas configurations. Right? So this one is more covalent. This one is first one is more covalent. Second one is less covalent or ionic. So this type of question they will ask me. So regarding to electronic configuration. So polarizing power. So that one is more regarding to pseudo inert gas configuration. Actually, 3 types of configurations are there. So what are the 3 types of configuration? Inert gas configuration. Inert gas configuration NS2 NP6. Pseudo inert gas configuration. Pseudo inert gas configuration NS2 NP6 ND10. Next, another one is non-inert gas configuration. Non-inert gas configuration. So what is this one? Non-inert gas configuration. NS2, NP6, ND10, NS2, NP6. This one is ND10. ND10, N plus 1, S2. Or N minus 1, S2. N minus 1 P6, N minus 1 D10, NS2. This configuration, non-inert gas configuration. So here, what are the examples? Regarding to examples, you take here. First one is inert gas configuration. K plus, Na plus, potassium, 1A group, 2A group, cations. Pseudo inert gas configuration example. Copper, Cu plus, silver, Rm. So zinc, cadmium, mercury. Like that. So non-inert gas configuration. This is whatever that one is P block elements. P block bottom side it is that one. That one is what is that one? Thallium Tl plus. So next that one is tin carbon silicon germanium tin lead Pb plus 2. So bismuth Bi plus 3. So like that here, these are the three different type of electronic configurations. So here pseudo inert gas configuration more favorable covalent nature. Next to this one, least to this one. Inert gas configuration favorable ionic bond formation. Getting this one. So is it clear? Any doubt regarding to this concept? Hello. So generally polarizing power is more, covalent nature is more. Polarizing power directly proportional to covalent nature. So is it completed? Completed means press the button. Next one. I think that one already explained that one in 1A group, 2A group regarding to thermal stability and solubility. That condition already explained that one. So here that one is we take here based on polarizing power only. We can explain that one colors. That one is thermal stability, solubility, nature of oxides. All these properties we can explain that one based on polarizability. Suppose colors we take here. So AG of AgCl, AgBr, AgI. What is the color? Covalent nature increases. Covalent nature is increases. Color increases. So AgF is white colored compound. AgCl. AgF we don't compare that one. AgCl is white color. So AgBr that one is light yellow. This is light yellow. So AgI, what is that one? Dark yellow. This one is dark yellow. How we are explaining these colors? So here, what is that one? Chloride, bromide, iodide, chloride to iodide. So covalent nature increases. Covalent nature increases. So that's why here, what happened that one? Color intensity increases. Silver chloride, almost all colorless compound. White color means colorless. But silver iodide, dark yellow color. What is the reason? Iodide ion polarizing power, that is more. Polarizability, not polarizing power. Polarizability of iodide ion is more. Covalent nature is more. Thermal stability, already explained that one. Thermal stability regarding to big size is there. So that one is thermal stability is more. Cation and anion almost all equal sizes. Thermal stability is more. Unequal sizes, thermal stability less. So here thermal stability, based on thermal stability, tell that one. So among the following, so here given lithium carbonate, sodium carbonate, lithium, sodium, potassium carbonate, cesium carbonate, which is thermally more stable. Lithium carbonate, sodium carbonate, potassium carbonate, cesium carbonate, which compound is thermally more stable? Tell the answer. So what is the answer correct here? Lithium carbonate, sodium carbonate, potassium carbonate, cesium carbonate. You take here option number 1, option number 2, option number 3. Which is more stable? Anybody open to all? Dharnivalan. Which is more stable compound? No, concept clarity is not there for you. So actually, what is that one? Already I told you previously. So what is the concept here? This one is regarding to ions. This is sizes, based on sizes. Polyatomic ions, big size. Big size, you take that one. Big size is polyatomic ions, carbonate, sulfate, phosphate. So like that here, this is polyatomic ions. Small size, what we are taking? Small size, halides, oxides, nitrites. Cation and anion both are big size, thermal stability is more. Right now you can apply that one. Big size cation, big size anions, thermal stability is more. Lithium carbonate, so potassium carbonate, cesium carbonate. So which is more thermally stable? Carbonate is big size, big. More thermally stable which condition? Which one is more thermally stable? Among these three compounds, which one is thermally more stable? Which one? Cesium carbonate. Least thermally stable, which one? Lithium carbonate. Very good. Suppose we are taking here lithium oxide, sodium oxide, potassium oxide, rubidium oxide, cesium oxide, which is thermally more stable? Which is more thermally stable? Very good. Why? Because oxide is small cation is required. Lithium oxide is thermally more stable. That is a very important point. Okay. So actually, simple technique I am telling here. Big size anion, big size cation is there, thermally more stable. Small size anion, that condition, small size cation, that is thermally more stable. That is very simple concept. But according to chemistry, we can explain differently. Here we can stability, small size condition, we can explain that one based on lattice energy concept. See here, compare that one, lattice energy. Lattice energy is more, thermal stability is more. See, lattice energy formula directly proportional to Q1, Q2. Inversely proportional to size of cation and anion. So lithium cation size is smallest, lattice energy highest. Lattice energy is more, thermal stability is more. This is thermal stability is more. Lattice energy directly proportional to thermal stability. So lattice energy highest which condition? Lithium oxide. Highest lattice energy, highest thermal stability. Big anion, big size condition, don't apply lattice energy concept. Here we can apply polarization concept. Here polarization concept. Polarization. Here lattice energy concept. Suppose here what that one is polarization. See, suppose here lithium cation and another one is cesium cation. So which condition polarization is more? Polarization depends upon size. Size of cation is small. Small size, polarization more. More polarization, more covalent nature. More covalent nature means less stable. Getting? So that is polarization. Polarization. Directly proportional to covalent nature. Covalent nature inversely proportional to thermal stability. So here this compound, suppose carbonates, sulfates, phosphates, how that is, for example, cesium carbonate is more stable, lithium carbonate least stable. How we explain lithium carbonate? Lithium carbonate condition, lithium cation is there. Lithium cation polarization is more. Polarization is more means covalent nature is more. Thermal stability least. That is the original concept. Simple trick what I am telling. Cation is big, anion is big, thermal stability is more. Cation is small, anion is small, thermal stability is more. That is trick. Concept is this one. Anion size small is their lattice energy concept. Anion size is big is their polarization concept. You apply that one. So polarization means size of anion is more, polarization. That is size of cation. Size of cation is small, polarization is more. Polarization or polarizability, two terms are there. Or polarization or polarizing power. Polarizing power. Polarizing power is regarding to cation. Polarizability regarding to anion. Any doubt? Any doubt, my dear? Thermal stability concept, what is that one? Very simple trick. Cation size is big, anion size is big, thermally more stable. Cation size is small, anion size is small, thermally more stable. Which anions is small size? So like that, very simple. Simple ions, halides, oxides, nitrates. Which is big size? Polyatomic ions, carbonates, sulfates, phosphates, oxalates, nitrates, hydroxides, like that. So this model definitely they will ask here NEET exam question. Any doubt here? Any doubt? This is already explained here in 1A group elements, that concept. Suppose here list of compounds they are giving. Beryllium carbonate, beryllium, magnesium carbonate, cesium carbonate, beryllium, magnesium, calcium carbonate, strontium carbonate, barium carbonate. So you take here strontium carbonate or barium carbonate. This is 2A group carbonates. 1A group you take here lithium carbonate, sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate. So here list of compounds 1, 2, 3, 4, 5, 10 compounds are there. Which is thermally least stable, which is thermally most stable. First question, least stable. Second question, most stable. Tell the answer. Open to all. Most stable or least stable? Anybody? Hello? Which compound is least stable? Anybody, ma? Least stable. This one is. So you take here. This one is compound number 1. This is 2, 3, 4, 5. This is 6, 7, 8, 9, 10. Which compound is least stable? Six is least stable. Very good. Why? Cation is big, anion is big. All condition anion is common. Smallest size cation B. Which is topmost stable? Topmost stable, which one? Very good. Cesium carbonate. Achana, correct answer. This is big size. Among all, this biggest one is this one, cesium. And compared to cesium, barium size is small. So here cesium carbonate, topmost stable, least stable barium carbonate. Very good, man. So like that here, conceptual questions. We have to practice that one. Thermal stability. That's why here 1A group carbonates, lithium carbonate only decomposing. Lithium carbonate on heating decomposes to lithium oxide and CO2. But sodium carbonate not decomposing. Potassium carbonate not decomposing. The potassium carbonate, rubidium, cesium, the carbonates not decomposing. Only lithium carbonate only decomposing. Similarly, you take here, so sulfates compounds. Sulfates on strong heating, what we are getting? Metal oxide and SO3. Okay, this is below 1073 Kelvin. Above 1073 Kelvin, so what we are getting? Metal oxide, SO2, O2 also you are getting. Metal sulfates. Suppose here lithium sulfate, you apply that formula. Lithium sulfate is there, Li2SO4, or magnesium sulfate, you take that one. Magnesium sulfate on heating, what you are getting? Less than 1073 Kelvin. Magnesium oxide plus SO3. Some exceptional cases are there. Exceptional cases means FeSO4 7H2O. This is on heating, giving FeSO4 loss of water only takes place. Suppose you are taking here 2 moles FeSO4. So this is heating. You are getting Fe2O3. Fe2O3 plus SO2 plus SO3. These two are exceptions. So generally metal sulfates heating below 1073 metal oxide SO3. Above 1073 metal oxide SO2 O2. Regarding to this is thermal heating. Similarly, nitrates also you take here. Nitrate compounds. Nitrate compound means what is that one? Metal nitrate. Metal nitrate. Generally, metal nitrates. Metal nitrate heating, what you are getting? Metal oxide. Metal oxide, NO2, oxygen. So example here you take that one, magnesium nitrate. Magnesium nitrate heating, what you are getting? So magnesium oxide, NO2, NO2, O2. Lithium nitrate also giving same. Lithium nitrate heating giving to lithium oxide, NO2, O2. But here other 1A group nitrate. And other 1A group nitrates means sodium, potassium, rubidium, that nitrates are different. So this nitrates MnO3. M is equal to except lithium. So heating what you are getting MnO2 plus O2. So here M is equal to other than lithium. Sodium, potassium, rubidium, cesium, like that. These are not giving to oxides. Lithium, that one is a diagonal relationship with magnesium. That's why heating of lithium nitrate to magnesium nitrate giving same type of products. But the other group nitrates, other 1A group, except lithium, sodium, potassium, rubidium nitrates, on heating giving to metal nitrite and oxygen. Metal nitrite and oxygen. Getting? Right? So like that here, MnO3 means what is that one? So MnO3 means here you take here lithium nitrate. This is except lithium, sodium nitrate like that. So you take here sodium nitrate, that one. But a heavy metal oxide, suppose heating, heavy metal oxides, this condition is different. We are getting the metal plus oxygen. Heavy metal oxides, heating, giving to metal and oxygen. Heavy metal oxide condition. Similarly, you take here bicarbonates, metal bicarbonates. Like that here MHCO3 heating, what we are getting? So that is metal carbonates, M2CO3 plus H2O plus CO2. So example, you take here lithium bicarbonate heating. So what you are getting? Lithium carbonate, Li2CO3 H2O plus CO2. So here all these reactions regarding to thermal stability. So regarding to thermal stability, they will ask here any type of question, which is thermally more stable, which is less stable. So why lithium carbonate is less stable, sodium carbonate more stable. So on heating, which compounds we are getting? These are all application questions regarding to thermal stability. So you have to compile that one, all that equations, whatever there in groups regarding to chemical bond. Getting. So after thermal stability, next concept is solubility concept. So metal bicarbonate heating, metal carbonate H2O CO2. Example, lithium bicarbonate, that is heating giving to lithium carbonate. So lithium bicarbonate, lithium cation, very small size. Polarizing power is more. That's why lithium bicarbonate is existing as a liquid. But other bicarbonates, 1 year. Completed. So next is solubility concept. Last concept today, solubility. Very simple, man. Solubility concept, how to apply that one? Solubility. So generally solubility. Here this concept is based on hydration energy and lattice energy. So hydration energy formula, lattice energy formula, both are same. That is equal to Q1, Q2 divided by radius of cation and radius of Na. Lattice energy formula also same. Q1, Q2, that is equal to Q1, Q2 divided by radius of cation and radius of Na. But here regarding to lattice energy and hydration energy greater than lattice energy, soluble. So wherever lattice energy is greater than hydration energy, salt is insoluble. Both are equal. Solubility of the salts. Solubility of the salts. So here regarding to solubility condition, suppose here you take here beryllium sulfate, magnesium sulfate, beryllium, magnesium, calcium sulfate, strontium sulfate, barium sulfate, like that. Barium sulfate is insoluble in water. Barium sulfate is insoluble in water. So what is the reason? Insoluble means lattice energy greater than hydration energy. Lattice energy greater than hydration energy. This is insoluble or partially soluble. Beryllium sulfate is more soluble in water. Soluble means answer. Hydration energy greater than lattice energy. You apply that concept. Getting this point? So here regarding to solubility, here also concepts are there. So here, which condition solubility increases, which condition solubility decreases in groups. That is, depends upon size. So big size cation, small size anion, Big size anion, you take that one. Big size, where that one? Carbonate anion, sulfate, phosphate, nitrates, like that. Big size. Here halogens, big size, you take iodide, bromide. So this one is big size. Getting? So big size anions. Small size means small size here, halogen, small size, chloride, and also you take hydroxide also small size regarding to solubility condition. Fluoride, you don't take here regarding to thermal stability. Thermal stability, all halides are small. Solubility condition, small size, chloride small, iodide, bromide big. Thermal stability condition, hydroxide also big. Here hydroxide is small category. So hydroxide, so next to oxide, nitride, remaining is same. So this condition, so wherever that one is small size anions are there. Small size anion condition, top to bottom solubility increases. So here this condition, second condition, any group top to bottom in any group solubility increases. Here top to bottom any group solubility decreases. This one is except 1A group. 1A group top to bottom carbonate solubility increases. 1A group top to bottom solubility of carbonates increases. That is exceptional case. So like that here, based on this concept, we can explain the solubility. Already I explained that one in here your class, regular class. So it is requirement is there, I can explain that one. Okay, ma. Right now time is over. Can I stop that one? So this is the solubility concept. Right? So any doubts? Okay, ma. Right now stop that one.